So thank you so much for inviting me to give a talk in this session. So today I'll talk about how do we understand urban activities with graph-based modeling. Well, you know, this is actually a picture a while ago. I took this from the internet, where a lot of the activity around us right now is actually basically online. When you look at this, what can you think of? What sort of activities? Anybody?
Maybe travel, airline travel.
Yep, could be online travel. What else? What sort of visualization is it? My stuff's normally very interactive, so I need people talking to me. I mean, this is much easier when we are in the physical room, right? I get people, I just point out to people, what do you think?
Is it some sort of social media?
Yeah, that's right.
Community?
That's right, Stephen. So this was some sort of visualization of, I think, Facebook communities. And actually a lot of communities online. So some of these are already outdated. You don't see some of these social media platform anymore. But this was quite old. It's something about 8-9 years old now. Now, the thing is, I want to draw back your attention to actually the complex networks around us to be able to describe activities, human activities in cities, in regions, in a country, and they can come from a lot of different sources of information, not just social media, but also, just think about our life before COVID, right? In the morning, you get on a, before you get on the car, you have to check your traffic first. So the first thing is a traffic network, right? So you want to make sure, maybe you have to drop off your kids. My life story in the morning, usually I have to drop off my kids in school and in their daycare. And then I need to make sure I don't miss my train to the city. So I have to then also check the train network. How is it going, right? And where do I park? So there's another information there. I have to find out the parking information. And all this information, right? So, and some of this information now are publicly available. And if you can actually model them they are complex networks, but they're actually somehow interconnected, and they can actually describe the activities of our cities. Now, let's just, so I'm leading a group that I'm very privileged to basically mentor, supervise. So a group of PhD students, there are 8 of them. I have 3 postdocs, and our group called CRUISE, Context Recognition and Urban Intelligence. And we're very interested in understanding all these different behavior and activities, because we can actually understand patterns and context from all kinds of data streams. And when we can actually model them, there's a lot of intelligence we can draw from it to be able to inform a lot of activities and to be able to enable things like smart cities, smart transport, smart buildings, smart retail, smart energy, and you name it. So how do we then understand, sense this behavior, model them, and to be able to even use them to enable sustainable cities and communities? So this is basically, one of the things that motivate our research. So from dynamic spatial-temporal behavior, we can actually understand situations around us, and this is even more important these days, because with the pandemic, a lot of situations are changing all the time. So, for example, you've got lockdown, you've got different restriction rules. So you need to understand, that people from governments, from companies, they need to make informed decision about all these things. So how do we actually help them? And actually, an example of this is actually, we had a project 2 years ago now, it's completed. Our partner, Northrop Grumman USA, a defense company in US, they had really large scale trajectory sensor data, GPS, and they come from, all kind of moving vehicles, so flights, from anything that moves in the tarmac, right? So it could come from a flight, it could come from their catering vehicle. It can come from you know, the baggage trucks and all that. So how do you know from this very noisy trajectory that what's going on if we want to build a situational map? So first thing we need to do, we have to reconstruct the map. So and we actually model these because the data is very noisy. We need to first knowing which point connects to other points, right? So some of them actually don't even have any identifier. So we actually have to start classifying the different activity, where there's a parking, patrolling, landing, and takeoff example. And we need to know, okay, this is a much faster velocity, and we know this is actually a plane, not a vehicle on the ground, and stuff like that. And this is a very difficult problem, in fact. How do we actually build this, right? So how do we build this map? And the map is basically a graph. It consists of a graph with the nodes and edges. So how do we infer these edges, for example, right, from GPS points, to be able to, at the end of the day, generate a final map. So in our pipeline, we come up with a way to be able to describe these trajectory features and using basically CNN to describe these trajectory features. And we also come up with a new way of basically cleaning these edges that we actually infer. And based on that, we can come up with final map. And there are two case studies in our paper. You could have a look that basically the architecture itself could be applied to GPS data of basically buses roaming around Chicago downtown. And you could see that the previous, I don't know if you could see my cursor here, but the closest state-of-the-art work, what they reconstructed is pretty messy, where this is actually our method. We could actually reconstruct the map quite nicely just from these noisy GPS points using this architecture. And in here, what you could see also, this is an airport tarmac map. We could reconstruct the map. So this is an example of how you can use information, how you can use and utilize like graph structure to be able to reconstruct some kind of like baseline situation map in a city. Now, the next thing I like to go is actually related to the previous talk. So I'm glad I'm speaking after the previous speaker. So it's about predicting when and where crime will strike next. So in here, we basically draw ideas from there's a lot of work on crime prediction, predictive policing and all that. And what they've done a lot is they use historical crime data to predict where crime will hit next. Now, we're very interested in understanding what are the factors influencing crime, and there are a lot of theory from crime theory, basically, where, you know, actually crime hotspots are actually also very influenced by, you know, the human behavior of the crowd, right, or where the crowds are and stuff like that. So and visitors. So we're very interested to understand how do we actually, is there any relationship, is there any correlation between you know, where people are and where crimes are? And we actually then use Foursquare check-ins, so location-based social media check-ins, as one of the source data, and we analyze it along with crime pattern in multiple cities, in Brisbane, in New York, and Chicago. And we actually managed to improve crime prediction at the next time period. So let's say if we train the model to predict the crime every 3 hours, we basically did that. So for every single location or region, let's say is it a block, is a neighborhood, whether there's going to be crime the next 3 hours or the next hour, and for every single type of crime, whether it be an assault, whether it's actually alcohol-related crime, or is it a theft, or is it a robbery, and things like that. So we had several papers about this, and we found, you could see there's very interesting relationships also in that paper about understanding different types of, like, you know, the entropy of visitations, of, let's say, if there's a certain pattern of, let's say, co-visitation of, let's say, a pub and a bank or whatever, you know, whether that actually has any relationship with, and also the density of those POI types, whether they have any relationship with certain type of crime in the area. And also another paper we also wrote about is, what is interesting is the movement of users also is important to be mined. So so in here we actually treat the information as undirected graph, but in here we actually treat the directed graph as an important source of information, because the flow of users, you know, if users tend to check in from one location to another, and we see that they like those who tend to visit safe areas, they always revisit safe areas, whereas those who actually like to you know, I mean, are open, or maybe not like, but they tend to revisit higher risky areas. They tend to revisit higher risky areas, and we found several patterns, and flow of movement pattern between morning and afternoon. If they change, they can mean something different. So for more information, check the paper. So when you actually understand all this dynamic spatial temporal behavior, and you can understand and derive a lot of insights, it can of course then help smarter planning and governance, especially you know, for, let's say, the local governments or police officers. So an example also of how you treat sensor data or sensor network in city from Internet of Things as part of the complex networks that you could actually learn from. In here, another example in our collaboration with City of Melbourne is actually parking sensors. So if you're not aware of the parking sensors in Melbourne CBD, they are available. The data are available as public data now, open data for now already more than 5 years. So we were one of the first group who worked with this data. So in 2016, they released it to us first. And we actually learned the different patterns of hotspots, and these actually hotspots of parking violations. It's not just hotspots of where you can get your parking, but it's parking violation, because back then, the City of Melbourne, they want to understand whether, you know, they need to tweak some of the parking rule, whether it's 2p or 1p and stuff like that. So they need to understand all that, and also understanding how to actually optimize the routing of the parking officers. So based on that, we can actually model both the parking node itself as part of the graph. And then you can then basically optimize the routing of the parking officer. We call this multiple traveling officer problem, because then what is really hard about this is actually an NP-hard problem, because the map state is keep changing, and there are thousands of parking bays to be monitored, and the parking officers need to collaborate. So we model them this as like a more theoretical problem called multiple traveling officer problem. And because the state of the graph keeps changing, it needs to be, you know, the model has to be updated really frequently. So we have, the details are in several of these papers, if you want to know more. So you could see why this can be modeled in such a way. So you've seen as examples from monitoring. I guess I don't have much time left. Let me just quickly show you one more thing about community detection. So we can also do a lot of work using sensor data, even if we don't have information about the data. So people move all the time, and we can actually, sometimes people don't reveal where they are. So, but how can we discover you know, people's locations, for example, and the pattern they move from, you know, this is actually important for example, for planning purposes, for knowing when you know where people are going to be, then you can actually optimize the resources and stuff like that. Now, how do we then detect, for example, community from, let's say, connectivity data, Bluetooth data or Wi-Fi data? And actually, this is quite an old work. This is actually 5 years ago. And we revisited this kind of data sets because of the recent work needed for contact tracing. Now, there's a lot of data around us, pervasive signals. So it could be from Bluetooth, people connectivity. So you don't even need to reveal, for example, that you are connected to, you're in this certain GPS location, but can we actually find out whether there are communities? So this is important because then if we know, for example, the you know, how many communities or how many groups there are, we can then profile them for future planning as well. Now, and this can be done in a privacy preserving manner, which means people don't have to share their location. Now, there's a lot of information that you can use to characterize this grouping behavior, and a lot of them based on their context. So people can be grouped based on certain context. So maybe you know, you and I are now grouped together within this because we are in the same meeting room, or, you know, maybe we could be grouped as basically family members because we always share a location, which is home, or you could be grouped together based on certain activity because maybe you are a gym member or things like that. So I'll just skip this. Just really briefly, normally when you actually have to sample a community, you have to first sample a context, and you want to see the normal distribution, whether they share the same context. And based on that, you first sample the activity, and then you look at the social interaction context. Whether once you have the activity context, then you look at the multinomial distribution to be able to infer the social grouping. Now, these are normally two-stage process, but in this paper, we did the sampling simultaneously. So in the literature, communities are a group of people that normally collocate together, or they interact quite regularly at the same time. So we used two-step approach in doing this. First, the discovering a context using topic modeling, and then we did clustering. I'll just skip the details. You can see the details in the paper. But some examples from the reality mining data set, for example, this is data collected from a campus in MIT. We just use Bluetooth signals to be able to extract groups. So we remove the ground truths of the groups. And based on the multinomial distribution that we have sampled, we can then discover these different groups, basically whether certain users are actually saying like, I'm part of ML grad, I'm part of Sloan group, and just using an unsupervised approach. So by doing this context sampling and community sampling, we actually can discover these groups. And this is actually done through Bluetooth data. We can discover these communities and how they're grouped together. And what you see here, the C here are basically context labels, which are basically, you know, the cluster labels that are assigned by the sampling. We don't know what they are, but they are basically done through the sampling. And we can do this as well on Wi-Fi data, for example. Again, this is data collected by Dartmouth College. So can we actually discover people's location just based on their access point connectivity, and whether we can actually extract their group based on that? And our method actually outperform all the other methods as well. Now, based on that, you can see this is quite an old work. And then when COVID hit and there's a need for contact tracing, we found that whether we could redo this kind of study for both purpose of can we actually, if let's say we inject the epidemic model to some kind of Bluetooth data, and see if one person is positive within all these Bluetooth traces, can we actually first detect it, but make it in such a way that, you know, when you get a notification in decentralized mobile contact tracing application, it's privacy preserving. So we then check both aspects of privacy and also utility in these kind of cases using Bluetooth data. I think my time is up. I won't be able to talk about this work, but just very quickly, because data have become really huge. If you have large scale data and you need to be able to perform graph operations on them, and check out this work. We have made the code available. Just in summary, we basically can compress a really large graph and come into smaller one while preserving the characteristic of the graph, and we perform alignment on them. So, which means you can then still perform the same operation on the compressed graph and to give you the answer that is an approximate, but at the same time, you know, it's going to be much faster. So we've done this over different data sets, including communication network, social network, co-authorship network, and we found that our method is not just fast, but also has high accuracy. And that's the source code. So I think I'll stop there, and I'll have to skip this part here. So thank you. That's my group. So they've done a lot of work. I'm actually presenting some of their work. Thank you.